All right, hello class. Um, Today we are working on our last um, E&M free response. Tomorrow I'll be switching over to mechanics. Um, and then the AP exam, if you're taking it, is a week from Monday. So that's exciting. Um, I think I'll give you guys maybe like some kind of a mock final exam. I don't know. Maybe I don't know what I'm going to do, but we'll do some after the AP exam. We'll probably take a couple days off, and then we will do some advanced stuff, just whatever I come up with. Okay. Hey Tim. Uh, hey Justin. Thanks for watching. Um, all right, let's get to it. Let's get to physics. So, what do we have for this one? Question one. You can already tell that's Gauss's law, right? You got spheres. Number one says a solid plastic sphere of radius A and a conducting spherical shell of inner radius B and outer radius C are shown in the figure above. The shell has an unknown charge. The solid plastic sphere has a charge per unit volume given by rho equals beta times r, where beta is a positive constant and r is the distance from the center of the sphere. Express your answers to A, B, and C in terms of beta, r, a, and physical constants as appropriate. So A says, consider a Gaussian sphere of radius r concentric with the plastic sphere. Derive an expression for the charge enclosed by the Gaussian sphere for the following regions. So no matter the region, we're going to use the expression integral of rho times 4 pi r squared dr. So that is the, hey Alex, hey Luigi. So that is the general expression when you're trying to calculate charge enclosed. So if I do that, I get the integral of beta times r times 4 pi r squared dr, okay, which is 4 pi beta times the integral of r cubed dr. Okay, so for part I, what the heck, we have Chris Martinez here. You do not apply Snell's law. You apply Gauss's law. This is AP Physics C, Chris. So nice to see you here. Got a former student showing up. That's always nice to see. Last week it was Nathan Hoyle. This week it's Chris Martinez. So doing that integral is going to give me pi beta r to the fourth power. Okay, so that's in the plastic conducting sphere region. Once we go outside the plastic conducting sphere, our Gaussian sphere is going to be enclosing all of the charge in the plastic sphere. So this is the charge enclosed as a function of r, but once we make our Gaussian surface big enough, it encloses everything that's in the plastic sphere. So what we should do is the charge enclosed would just be the charge enclosed evaluated at A. So you get pi beta a to the fourth. would be your answer there. Okay, part B. Hey, Alex. Thanks for tuning in. Use Gauss's law to derive an expression for the magnitude of the electric field in the following regions. So Gauss's law says that the integral of E dot dA is equal to charge enclosed over epsilon naught. And then because it's a spherical Gaussian surface, this is just going to be E times 4 pi r squared. So we're going to take this is going to tell us that the electric field is charge enclosed over 4 pi epsilon naught r squared. So we can see if we take this expression and we plug it in for our charge enclosed, we're going to get beta r squared over 4 epsilon naught. I think pi's cancel, yeah. And for the other region, I'm going to use this expression for the charge enclosed. So that would give me beta a to the 4th divided by 4 epsilon r squared for the second region. At any point outside of the conducting shell, it is observed that the magnitude of the electric field is 0. Determine the charge on the inner surface of the conducting shell. Okay, so we know that it's a conducting shell, and the electric field inside of a conductor is 0. So basically, if let's say this is the plastic sphere, and here's the inner edge of the conducting shell, and here's the outer edge. Okay, and if we have a Gaussian sphere, hey Rowan, if we have a Gaussian sphere that is in the conducting shell, it's going to give an electric field of 0. So this has a positive charge, and so the inner surface of the conducting shell has to have the same charge but negative. Okay. So I would say that the charge on the inner surface is going to be minus pi times beta times a to the 4th. Okay. Then for part 2, it says determine the charge on the outer surface of the conducting shell. And notice how it says that the electric field is 0 even outside the conducting shell. So that means that we still have to enclose 0 charge, even if our Gaussian surface is out here. Okay. Now, because I already enclosed 0 right here, and if I have a Gaussian sphere out here, it still encloses 0. That means that the outer surface doesn't even have any charge. So I would say that the charge on the outer surface is 0. D. On the axes below, sketch the electric field as a function of distance r from the center of the sphere. So we can see that we have an r squared dependence, and then we have a 1 over r squared dependence, and then we have an electric field of 0. So when we graph that, it's going to be r squared, which looks like a parabola, then it's going to look like 1 over r squared, which looks like this, and then it's going to drop to 0. So this would be A, B, C. James, we won't get magnetic until problem 3, I'm guessing. All right. 2 says, the figure below shows the sphere and shell in 4 points. Point W is at the center of the sphere. Point X is on the surface of the sphere. Points Y and Z are on the inner and outer surface of the shell, respectively. Rank the points according to the electric potential at that point, with 1 indicating the largest electric potential. So if you're close to a positive charge, you have the largest electric potential. Okay? So W is going to have the highest electric potential because it's at the very center of the positive charge. So this is number 1. X is the next closest, so it's going to be number 2. And then the electric field is between Y and Z is going to be 0. So there's no potential difference between Y and Z. So these are both number 3. All right. So question 2 looks like a capacitor, doesn't it? An experiment is designed to measure the dielectric constant of paper that has an area of blah using aluminum foil. 2 parallel plates are created with the same area as the paper. We should make a capacitor sometime. We should make a capacitor at home. 500 sheets, 500, whoa, that's a lot of paper. A ream of paper is placed between the aluminum foil plates to create a capacitor as shown. Using a multimeter, the capacitance of the capacitor is measured. The number of sheets and the total thickness d of the stack of paper are recorded. The experiment is repeated, reducing the number of sheets of paper each time. Blah. Okay, so A says, indicate the quantities which should be graphed to yield a straight line whose slope could be used to calculate the numerical value of the dielectric constant of the paper. All right, so we learned an equation for capacitance for a parallel plate capacitor. It's epsilon A over D. All right? So we want to get a straight line. So notice how I have capacitance equals epsilon times A times the quantity 1 over D. So if we let 1 over D equal X and we let capacitance equal Y, then the slope is going to be epsilon times A. So what I would say is on the vertical axis, I would put the capacitance. And on the horizontal axis, I would put 1 over D. All right? So I need to compute my 1 over table. 1 over 0.045 is 22.2. So let me fill out my table. 22.2, 1 over 0.036, 27.7, 1 over 0.027, 37. 1 over 0.018 is 55.5. And 1 over that is 100. So these are my points. Maybe I'll put some spaces into. There. So it's kind of lined up. I'm guessing that I'm going to graph it next. What do you guys think? You think I'm going to graph it next? Let's see. Oh, I'm going to plot all the points. Awesome. So I'll put capacitance, all right, in farads, all right, and then I can see that my 1 over d goes all the way to 100. So on here I have 1 over d on the horizontal axis. Okay, and I'll put 100 here. So each of these boxes is worth 20. Or yeah, and then it looks like my capacitance goes up to 21 times 10 to the minus 11. So I'm going to have each one be 4 times 10 to the minus 11. Four times 10 to the minus 11. Okay, so I'm not going to do the times 10 to the minus 11. So let me graph my points. Looks like I got 22.2 and then 6.5. So 22 and then 6.5 will be right here. We got about 28 and 7.4. Oh, I screwed up that, didn't I? Because this is 20. This would be 40, so this would be 24. So it's going to be like this. And then my next one is 28, 7.4. And then my next one is 37, 8.9. Oops, around here. And my next one is 55, 11.9. So 55 might be right here. 11.9 is like right here or so. And then the last one is 100 and then 21. So 100 and then 21 is like up here. So this is our straight line. Oops. So one of the things you can see is that this does not have an intercept of 0. So that means that there's some kind of a systematic error. Okay. But so we did part B. Now we do part C. Part C says, using the straight line, calculate the dielectric constant for the paper. So I can see that my slope, it goes over roughly 5 boxes. So the run is about 100. And the rise, it goes from maybe 4 to, it rises roughly 4 boxes. Okay. So that would be 16 times 10 to the minus 11. So my slope is going to be 1.6 times 10 to the negative 12. And that equals epsilon times the area. Let me make sure I did that right. Yeah. And the area, it says, is 0.06. So I have 1.6 times 10 to the minus 12 divided by 0.06. And I get that epsilon is equal to 2.7 times 10 to the minus 11 farads per meter. Okay. Now that looks like they're pivoting to, they're pivoting to an RC circuit. Student now makes a capacitor using aluminum foil plates and just one sheet of paper. Using the experimentally determined dielectric constant, the student calculates the capacitance to be 18 nanofarads. Student uses this uncharged capacitor to build a circuit using a wire, 36 volt battery, and 3 identical 80 ohm resistors. And an open switch. Calculate the current immediately after the switch is closed. So one of the things I've kept saying is that if you have an uncharged capacitor, it behaves like it has no resistance at first. So the total resistance in our circuit is going to be 80 in parallel with 80, which is then in series with 80. And if you work that out, it's 120 ohms. And then the current would be V over R, which would be 36 over 120. Oops. Which is 0.3 amps. Part E says determine the time constant for the circuit. Again, the circuit has, so tau, the time constant is RC. And we can see that the resistance in the circuit is 120 ohms. So I have 120 times 18 nanofarads. So 120 times 18 gives 2.2 microseconds. Students A and B measure the time it takes. Let me see if I have any questions. Students A and B measure the time it takes after the switch is closed for the voltage across the capacitor to reach half its maximum value and find that it is longer than expected. Student A assumes that the capacitance value is correct. Okay. Would student A conclude that the resistance value is larger or smaller than measured? So if it's taking longer than you expect, then that means that the time constant must be longer than you expect. And if you're saying the capacitance is correct, then that means your resistance must be wrong, and it has to be too big. So the resistance is larger um, than measured. What could account for this? One thing that could account for it would be the resistance of the wires. Okay. Another thing is the capacitor. There, maybe the piece of paper isn't completely. No, that wouldn't be it. It's got to be the wires. Part 2, student B assumes that the resistance value is correct. Would student B conclude that the capacitance value is larger or smaller than measured? Okay. Well, again, if you're assuming that R is right, then the capacitance has to be wrong. And that means that the capacitance is actually larger. Okay. So experimentally, what could account for this? Um, one of the things could be one of the things I told you about was the edge effect. So if you have the electric field in the capacitor plates, the electric field goes around like this, kind of. That would have the effect of increasing the capacitance. So I'm gonna say edge effect. Trying to think of something else. That's the only thing that's jumping out at me is just the edge effect. Yeah. It could be that if you just use one sheet of paper, um, so if you have a stack of 500 sheets of paper, there's going to be little air gaps between the pieces of paper, so the distance between the capacitor plates is going to be larger. Whereas if you have one piece of paper, there's no air gap, and so that is going to have the effect of making the distance a little bit smaller than you anticipated. So that could be another thing. I don't know. It's kind of an interesting question. I'm curious to see what the answer key says. Oh, maybe this piece of paper had an anomaly. That's another idea. All right. So we're going to go to number 3. Ooh, this is kind of cool. So the figures above represent different views of 2 long straight horizontal wires, 1 and 2 carrying currents I1 equals I2 equals 2I, respectively, in the directions shown. The wires are held in place. In figure 1, the current on the wire is directed out of the page, and wire 1 is a distance D above wire 2. Point P is a horizontal distance D from wire 1 and a distance D directly above wire 2. Express your answers in terms of blah. Use Amperes Law to derive an expression for the magnetic field of at point P due to wire 1. Amperes Law says that the integral of B dot dl equals mu naught times the current enclosed. Okay, So the current enclosed is just I, and then B dot dl is B times 2 pi r. But the radius of the circle is d. So we're going to get B equals mu naught I over 2 pi d. All right. Part B says derive an expression for the magnetic field, the net magnetic field at point P. So we've got wire 2 and wire 1. We have to add them as vectors. So the total magnetic field at point P is the magnetic field from wire 1 plus the magnetic field from wire 2. We got to add them as vectors, though, because they're not pointing in the same direction. Wire 1 is going to create a magnetic field that points upward. So we have mu naught I times or mu naught I over 2 pi d, and that's going to point in the plus j direction. All right, because that's upward. Wire 2 is going to create a magnetic field that is into the page. It has twice the current. All right. So into the page would be in the minus k direction. So we can see that the total magnetic field is mu naught I over 2 pi d times the quantity j minus 2k. So now we got to do the magnitude of this, and you can easily figure out using the Pythagorean theorem that the magnitude of j minus 2k is square root of 5. So that means that the magnitude of B is going to be square root of 5 times mu naught I over 2 pi d. C says calculate the numerical value of the angle to the horizontal for the direction of the magnetic field at point P. So we've got a magnetic field that goes up, and then into the page 2, okay? And so the total magnetic field kind of points like this, okay, according to the parallelogram rule. This is kind of a side view. So the total magnetic field is like this. This is 1, this is 2. All right? So if we want this angle, that's going to be the arctan of 1/2. Which is 26 degrees. Actually, 26.6 degrees. Wire 1 is now released. And my paper is released. Oh my gosh, it keeps... Oh my gosh, look at this. I thought I was almost done. I thought that was the last page. I was like, oh, here we go. We're home free. It's going to keep going. All right. I'm going to need another piece of paper, so I'm just going to get rid of this one. So this is the laborious one. So this is CHL 429 part 2. Okay, so what part were we on? We were on part D. So wire 1 is now released. Which of the following best describes the initial motion of wire 1 due to the magnetic field of wire 2? Assume gravitational effects are negligible. So wire 2 is creating a magnetic field that points into the page. Okay? So we can actually see that the magnetic field of wire 1, or sorry, the magnetic field of wire 2 and wire 1 okay. Actually, this picture is the best one for this. So wire 1 is creating a magnetic field that, or wire 2 is creating a magnetic field that points like this. Okay. Man, this one's kind of hard to visualize. I got to do the right hand rule. Basically, you want to do the right hand rule for this half of the wire, and then you want to do the right hand rule for this half of the wire. Okay, so I got my current going this way, and then I've got a magnetic field that points like this. So this part of the wire is going to have a force that goes that way. Okay, and then this one's got to go that way, and then magnetic field that points like that. Right. So this part of the wire is going to have a force that goes that way. So actually, it's going to spin. This wire is going to spin in the clockwise sense. Okay. Now, I'm not even going to do... Okay, fine, I'll do it. Wire 1 is now replaced by a conducting rectangular loop. The long side of the loop is put on the wire. The current I2 for wire 2 is decreasing linearly as a function of time. So we have a magnetic field that is into the page that is getting smaller. Okay? The fact that it's getting smaller means that a current is going to be induced, which is going to be in this sense. Okay? Because that would select the integration that will give the correct flux as a function of time. So we have so it is going to be this one. Why? Because this one has B. There's B, and there's the area, and it has the correct limits of integration. Take the derivative of this to get the current, or to get the EMF, and then divide by resistance to get the current. I already answered the direction of the current is going to be clockwise. All right. So anyways, that was that. Question 3 was the laborious one. All right. Thanks for watching, everyone. Sorry that went a little bit long. I will see you tomorrow with mechanics. Exciting.